Hello, and welcome to Badger Talks Live, which brings exciting happenings, resources, and talent from your UW flagship campus to the people of Wisconsin and beyond. I'm Brooke Cotton from Central Minnesota, and I'm a third-year undergraduate student in the astronomy department at UW-Madison. I am pleased to introduce Melinda Soares Furtado, NASA Hubble Postdoctoral Fellow. Melinda will share how observational signatures are left behind when stars consume their own close-orbiting planetary companions, an event that is fairly commonplace in the universe. Today, we will learn about currently known paths to search for such events and why these cannibal stars play a critical role in our understanding of stellar and planetary astrophysics. Melinda Soares Furtado is a NASA Hubble Postdoctoral Fellow at the University of Wisconsin-Madison. She's investigating anomalous stellar signatures that arise from the accretion and engulfment of substellar companions. Melinda also applies image subtraction reduction techniques to photometric surveys in an effort to search for periodic variability in open clusters. When she is not glued to her terminal, you will likely find her perusing used bookstores for vintage textbooks or tending to her ever-growing plant collection. Please join me in welcoming Melinda Soares Furtado.
Thanks so much, Brooke, for that warm welcome. It's a wonderful honor and privilege to be part of the Badger Talk series and to talk to you today about worlds devoured, the idea that stars can actually ingest their own planetary companions, that this is not a rare phenomena, and in fact, some of our own inner rocky bodies await this very fate. So that's what I'll be talking about today. I'll be focusing on some of the work that my team is doing to look for these sort of ingestion sites, and I'll talk about future works as well. Okay, so it's important to get a sense of how stars evolve. What I'm showing you here is something called a Hertzsprung-Russell diagram, or an HR diagram, of a star system where the stars are all born at the same time, so they're coeval in nature. And what we're looking at is temperature versus luminosity. So brighter stars are up here, top of the y-axis, and hotter stars are here, lower on the x-axis. And when stars are born, they occupy this fairly diagonal feature known as the main sequence. Your lower mass cool stars down here at the bottom, sun-like stars somewhere here towards the center, and then your more massive blue, bright, hot stars. But they don't stay in these regions as they evolve. So what we're going to see is an animation. We're going to see stars aging, and as they age, they're actually going to evolve away from the main sequence. They're going to get cooler and brighter. And what's happening is that they're expanding in size. They're exhausting their core hydrogen supply, transitioning to hydrogen fusion in a shell surrounding the core. And the hydrodynamical response to that is an expansion. And that expansion is what often leads to these planetary engulfment events. This is why it's so important to highlight early on in my talk. So let's go ahead and watch these stars evolve over billions of years. Mind you, the sun at about 4 billion years, roughly close to 5, is still here on this main sequence. Hasn't had enough time to evolve away. So this takes quite some time. All right. We're just letting the clock go, and we'll notice that about 4 billion years, our blue stars are pretty well evolved off of the main sequence. And we're seeing now at 10, 11, 12, 13 billion years, still our reddest, coolest stars have not exhausted their core hydrogen supply. They live the longest time on that main sequence. And what's actually happening, and wasn't shown in that animation, is that as they're evolving off of the main sequence, they're getting larger in size, like I pointed out, and it can be quite a bit larger. In fact, the sun today is about 100 times smaller than the sun will be when it is a red giant, many billion years into the future. And so what does that mean, given what we know about exoplanets today? Over 5,000 exoplanets have been detected since the launch of Kepler and TESS, which led to the vast majority of those detections. If we combine the known exoplanet population into a single animation, this is taking everything that was known as of September of 2021, And we show the host star at the center. What we're getting a sense here is the orbital separation, the relative orbital separation of the vast number of exoplanets that have been detected. The overwhelming majority, over 90% of these, are evolving pretty sun-like stars, sun-like in terms of the mass and in terms of the age. And this has a lot to do with observational biases. We know a lot about suns and their close orbiting companions. But these systems will age, and those sun-like stars will expand as they run out of their core hydrogen supply. And in fact, that star will become much, much larger in size. A third of all sun-like stars have planets that will one day be engulfed. And this is specifically focused on the larger than Earth-sized planets with orbital periods about an Earth year or less. So this is not a rare phenomena, and it's still rarer less if we think about inner rocky bodies like Mercury and Venus, which are even smaller than the Earth. It is a fate awaiting the inner bodies in our own solar system. So if we look at a current sun today at about 4.6 billion years, and we think about the orbits of Mercury and Venus and Earth, we get a sense of where the habitable zone is here close to Earth and Mars. In the future, 12.5 billion years from the creation of the sun, that habitable zone will move far out as the star increases its luminosity, becomes much brighter, much larger in size. And in fact, the inner rocky bodies will be enveloped. Mercury and Venus will be ingested by this event. The fate of the Earth is a little more unknown and depends a lot on tidal forces, which are difficult to model. And some planets have already long been ingested by their aging stars. What sort of ingestion-derived observational signatures might they have left behind? Can we observe them? Can we measure them? And what can they tell us? There are 4 major tracers: changes in chemical abundance, changes in rotation. You can actually spin up your host star. You can also even reverse the rotation depending on whether you had a prograde or retrograde orbit that was ingested. You can actually produce transient events. You can change the brightness. You can also change the color of your host star. There was a really big discovery in Nature that showed one of the first planetary transient events that was observed by the Zwicky Transient Factory. And you might also be able to strip part of your star. Imagine removing the outer envelope of the star due to the incredible torque. So these are all things that can happen. I'm predominantly interested in the chemical enrichment signatures. So we'll focus a bit on that today. And what do I mean by the chemical enrichment signatures? Well, if we look at this plot of the abundance in a pristine meteorite, a calcium chondrite, this is basically an undifferentiated meteor, something like this, which has already fallen to Earth, so now it's in that meteorite category. And we get a sense of what that abundance is, comparing it to the abundance in the sun, thinking that these form from the same molecular cloud and should be overwhelmingly formed from the same initial stuff. Most of the species, therefore, follow this one-to-one line where they are identical. Not a terrible surprise that noble gases and volatiles, things that are easily lost if you don't have enough gravity to hold on to them, are more abundant in a more massive star and less abundant in chondrites. But there are species like lithium here, which are easily destroyed in the interiors of stars, but can survive in chondrites, in planets, even in brown dwarfs in some cases. And if ingested, you can enrich stars in these species. So thinking about lithium in particular, how statistically significant is a lithium enrichment event? If I was to ingest an entire gas giant's worth of material, an entire Jupiter, into a sun-like evolving star, are you going to get anything that's appreciable in terms of its observational signature? Is it so little mass that's being added that this signature is quite dilute and you don't have anything that's statistically significant? This is very much the question that we set out to answer, knowing a lot about what sort of lithium to expect in stars in their baseline, what nominal stars would contain. And so some work I did in 2021 asked this very question. We're looking again at one of these HR diagrams, effective temperature versus luminosity. And we're seeing star tracks. This is a 1 solar mass track, a 1.2 solar mass track. What's happening is that it's aging away from what would be the zero age main sequence. Imagine a diagonal line that connects all of these here, like we saw before. And here are these turnoff points where the star is now burning hydrogen in its, no longer burning hydrogen in its core, and it's evolving away from the main sequence. This is known as the red giant branch. What I looked at is if you were to ingest an entire gas giant's worth of material and you were stars of these varying masses between 1 and 2 solar masses. So imagine at this point, we have a sun-like star that is right here, just about to turn off of the main sequence. And imagine here, and we let it go ahead and swallow up a gas giant's worth of material. But imagine here we have the star a little bit more evolved. It's slightly larger now. And yet again, we're going to ingest a gas giant's worth of material. We do this for every single point plotted, thinking about every type of host star, and in each case, ingesting 1 gas giant. And we ask ourselves, how statistically significant is that signature going from a little less than 1 to 5 sigma? And what we see is that there was a pileup. There's a region here, a parameter space of host stars and ages pretty early from the main sequence turnoff point. So they're just now evolving off of the main sequence, just run out of hydrogen in their cores. But for stars between 1.4 to 1.6 solar masses near that main sequence point, you could get statistically significant 5 sigma statistical significance by ingesting a gas giant's worth of material. And that was very interesting to us. This was something that we predicted. And sure enough, it was something that just shortly thereafter in 2022 was observed in the LAMAST survey data set. What was observed was if you took just typical giants shown here in blue in a histogram and then overplotted here with this Gaussian, they had a typical mass that was a lot lower than the mass of the enriched giants. And in fact, there was a pileup that was in between this 1.4 and 1.6 mass range that we had predicted. So this was quite exciting to see this prediction was observed in the data. But lithium is just one tracer, and there's some difficulties with using lithium to back out how much mass the star might have ingested. Stars can also self-pollute with lithium. I won't go into that today because of time. So it would be wonderful if we could find other chemical tracers in addition to this. So what's next is we know that some planets have been ingested by their aging stars. Can we find them? And so I'm working with the team at the Michigan State University, led by Joey Rodriguez, to go and find these particular targets and to try to understand, secondly, how are the properties of these stars distinct from those that have not ingested planets? So that's something we're very interested in. In addition to that, are there other important chemical tracers like lithium that accompany planetary ingestion events? And might those tracers not have degeneracies? Might the stars not self-pollute in that way so that maybe we can even determine how much mass was ingested? And that brings me to this bottom point is what can we learn about the ingested companion? How massive is it? What is its bulk composition? What is the planet made of? What does that tell us about where it originally formed? Because those species might be different. We'll also learn a lot about anomalous stars, stars that are rapidly rotating and chemically peculiar, and get a sense of whether or not planets that are being consumed play some role in a subset of those anomalous stars. And so I just want to highlight Brooke, who did this wonderful introduction, is actually working on these 2 bottom questions. Are there other tracers? And what can we learn about the companion from the tracers as part of the Lamont REU program and part of an honors thesis here at the University of Wisconsin-Madison. So we've identified a target star that we believe to be an ingestion event, and now have a wonderful control sample of stars that are very similar in terms of the mass, the metallicity or the iron abundance, and the age. And we're trying to determine in what ways beyond lithium, we certainly see lithium enhancements, might they be chemically distinct? And we're very excited to see what we learn in this process. And with that, thank you so much for your time, and please feel free to post questions in the chat.
Thank you for watching this Badger Talks live event produced by the University of Wisconsin-Madison through UW Connect's outreach and the Office of State Relations. Follow us on Facebook and YouTube to see the library of past recorded talks. Please visit badgertalks.wisc.edu to see the schedule of upcoming talks, Sign up for the Badger Talks email list and search the roster of over 400 UW experts who are available to give talks on important issues in your Wisconsin community.